At 6:23 a.m. on October 14, 1942, Staff Sergeant Jake Murphy crouched beside a bone-dry aviation fuel tank at Henderson Field on Guadalcanal, watching 12 P-40 Warhawks that couldn't fly because there wasn't a single drop of 100-octane fuel left on the island. The 28-year-old motor pool sergeant from Amarillo, Texas, had spent 8 years working on Ford engines in Detroit before the war, but nothing in his experience had prepared him for what he was about to attempt with coconut oil and a chemistry set improvised from aircraft parts. Japanese bombers had destroyed the last fuel depot 3 days ago, leaving the 67th Fighter Squadron with aircraft but no way to get them airborne. The next fuel convoy wasn't due for 3 weeks, assuming it could fight through Japanese submarine patrols that had been sinking supply ships throughout the Solomon Islands. Meanwhile, enemy bombers attacked Henderson Field twice daily, methodically destroying American aircraft on the ground while pilots watched helplessly from their foxholes. Jake's commanding officer, Major Bill Harrison, had given him an impossible assignment: find a way to fuel 12 fighters using whatever materials were available on the island. No aviation fuel, no high-octane additives, no petroleum products of any kind, except what could be salvaged from wrecked vehicles. The major concluded his orders with grim reality. "Sergeant, we've got maybe 48 hours before the Japanese overrun this position. If those P-40s can't fly, we're all dead." Jake stared at the empty fuel tank and felt the weight of an entire airbase depending on his mechanical knowledge. Standard aviation fuel was refined petroleum with precisely controlled octane ratings, anti-knock additives, and performance characteristics that had been developed through decades of engineering research. He had palm trees, crashed aircraft, and automotive parts salvaged from destroyed vehicles. Everyone expected him to fail. The squadron pilots called his assignment impossible. Even the base engineers said there was no substitute for aviation fuel that wouldn't destroy aircraft engines within minutes. They were about to discover what happened when you underestimated a Texas mechanic who understood engines at a molecular level. Jake Murphy grew up on a cotton farm outside Amarillo, where mechanical problems couldn't wait for parts deliveries or manufacturer recommendations. When the tractor broke down during harvest season, you fixed it with whatever was available: fence wire for electrical repairs, leather belts for power transmission, kerosene for cleaning, and anything combustible for emergency fuel. His father, Sam Murphy, had been a wildcatter before farming, and he'd taught Jake that engines were just controlled explosions that would run on anything that burned if you understood the chemistry. The Murphy farm sat on 640 acres of Texas Panhandle, where mechanical reliability meant the difference between a successful harvest and financial disaster. Equipment failures during critical seasons could bankrupt the family, so Jake learned early that improvisation and mechanical intuition mattered more than following manufacturer specifications. Jake's earliest memory involved helping his father repair a broken-down Model T using spare parts cannibalized from a rusted-out combine harvester. The repair required understanding how different mechanical systems could be adapted for new purposes, using materials and techniques that Henry Ford never intended but worked perfectly for Texas farming conditions. These early lessons in adaptive mechanics shaped Jake's approach to problem-solving long before he encountered formal automotive training. He learned to study mechanical problems from multiple angles, consider unconventional materials, and develop solutions that worked with available resources rather than requiring ideal components. Jake's mechanical education continued at Amarillo High School, where he spent more time in the automotive shop than in academic classrooms. His instructor, Mr. Pete Rodriguez, was a former Army mechanic who had worked on everything from motorcycles to aircraft during World War I. Rodriguez recognized Jake's intuitive understanding of mechanical systems and encouraged him to think beyond conventional repair procedures. "Engines don't care what the manual says," Rodriguez told his students. "They only care about compression, fuel mixture, ignition timing, and lubrication. Get those four things right with whatever materials you have, and any engine will run. Get them wrong with the finest parts money can buy, and you'll be walking home." The philosophy proved invaluable when Jake moved to Detroit in 1934 to work for Ford Motor Company. The Rouge River plant produced thousands of vehicles daily using assembly line techniques that demanded absolute precision and reliability. But Jake's farm background gave him insights that factory-trained mechanics often lacked. While other mechanics followed standardized procedures and relied on specific replacement parts, Jake understood how mechanical systems could be adapted and modified to work under conditions that exceeded manufacturer specifications. He could diagnose problems that stumped other mechanics and develop repairs that used available materials rather than waiting for parts deliveries. His reputation for solving impossible mechanical problems led to assignment in the experimental engine division, where Ford was developing high-performance engines for military applications. Jake worked on prototype aircraft engines, automotive racing engines, and specialty applications that required mechanical innovations beyond standard production techniques. The experimental work taught Jake about fuel chemistry, octane ratings, compression ratios, and performance characteristics that would prove crucial when he faced fuel shortages on Guadalcanal. He learned how different fuels affected engine performance, what additives could improve combustion characteristics, and how engines could be modified to run on alternative fuels without catastrophic damage. But Pearl Harbor changed everything for Jake and millions of other Americans who found their technical skills suddenly needed for military purposes. The Army Air Forces desperately needed mechanics who could keep aircraft operational under conditions that exceeded anything experienced during peacetime maintenance operations. Military aircraft maintenance in 1942 required keeping complex machines functional under extreme conditions, with limited resources and constant pressure from enemy action. Standard procedures assumed access to proper replacement parts, specialized tools, and manufacturing facilities that could provide components designed specifically for each aircraft type. Pacific operations created maintenance challenges that exceeded anything anticipated during peacetime planning. Aircraft operated in tropical conditions that accelerated wear and corrosion. Spare parts had to be transported across thousands of miles of ocean controlled by enemy forces, and combat damage required repairs that weren't covered in any maintenance manual. Jake enlisted in January 1942, expecting assignment to a motor pool where his automotive experience would be valuable for maintaining trucks, jeeps, and other ground vehicles. Instead, he found himself selected for aircraft maintenance training, where his experimental engine experience qualified him for assignment to fighter squadrons operating in forward combat areas. Aircraft engine maintenance was far more complex than automotive work, requiring precision that exceeded anything Jake had encountered in civilian employment. Aircraft engines operated at higher speeds, generated more power per pound, and had performance requirements that demanded absolute reliability under combat stress. Training began at Chanute Field in Illinois, where Jake learned about radial engines, inline engines, superchargers, and fuel systems that were far more sophisticated than anything used in civilian applications. But his mechanical intuition and problem-solving experience gave him advantages that other trainees lacked. While classmates struggled to memorize maintenance procedures and part specifications, Jake understood the underlying principles that governed engine operation. He could visualize how different systems work together and identify problems through logical analysis rather than rote procedure following. His instructors recognized exceptional ability, but worried about his tendency to modify standard procedures based on field conditions rather than following regulations exactly as written. Technical Sergeant Williams wrote in Jake's evaluation, "Murphy demonstrates superior mechanical ability, but shows disturbing willingness to deviate from approved procedures. His innovations usually work, but unauthorized modifications could compromise safety and reliability." The assessment proved prophetic during Jake's early military career. After completing training, he was assigned to the 67th Fighter Squadron and sent to the Pacific Theater, where he would encounter maintenance challenges that couldn't be solved using standard procedures or approved replacement parts. The 67th Fighter Squadron was equipped with P-40 Warhawks, rugged fighters that were reliable under normal conditions but required constant maintenance when operating from primitive airfields in tropical climates. The P-40's Allison V-1710 engine was liquid-cooled, mechanically complex, and sensitive to fuel quality variations that could cause performance problems or catastrophic failures. Jake arrived at Henderson Field in August 1942, during the early phases of the Guadalcanal campaign, when American forces were still establishing defensive positions and building the infrastructure needed for sustained military operations. The airfield was a hastily constructed strip carved out of jungle with minimal facilities and no proper maintenance hangars. Aircraft maintenance had to be performed outdoors using improvised tools and whatever spare parts could be flown in aboard transport aircraft that faced constant threat of enemy interception. Jake learned quickly that Pacific operations required mechanical innovations that weren't covered in any training manual. His first major challenge involved repairing a P-40 that had taken battle damage to its cooling system during a dogfight with Japanese Zeros. Standard procedure required replacing the damaged radiator with an identical replacement part that wasn't available on Guadalcanal and wouldn't be for several weeks. Jake improvised a radiator repair using copper tubing salvaged from a destroyed fuel truck, welding techniques he'd learned at Ford, and cooling system modifications that restored the aircraft to operational status within 48 hours. The repair worked perfectly and remained functional for the remainder of the aircraft's service life. Word spread quickly through the squadron that Jake could solve mechanical problems that other mechanics considered impossible. Pilots began requesting specifically that he work on their aircraft, and commanding officers started assigning him the most challenging maintenance problems that couldn't be solved through standard procedures. But the fuel crisis that developed in October 1942 presented a challenge that exceeded anything Jake had encountered during his civilian or military career. Aviation fuel was a precisely engineered product with specific chemical characteristics that were essential for proper engine operation. Octane rating, volatility, combustion characteristics, and additive packages were all carefully controlled to ensure reliable performance under combat conditions. The shortage wasn't just inconvenient, it was potentially fatal for everyone on Henderson Field. Without functioning aircraft, the airfield couldn't defend itself against Japanese bombing attacks that were systematically destroying American facilities and personnel. The next major enemy assault would likely succeed unless the P-40s could get airborne to intercept attacking bombers. Standard military protocol was clear. Aircraft engines must use only approved aviation fuels that met precise specifications for octane rating, volatility, and performance characteristics. Using unauthorized fuels could damage engines, compromise safety, and result in court-martial for any mechanic who violated fuel regulations. But Jake had learned enough about fuel chemistry during his experimental work at Ford to understand that engines would run on anything that burned properly, provided the fuel mixture and ignition timing were adjusted to compensate for different combustion characteristics. The island offered limited resources for fuel improvisation, but Jake had noticed something during his daily walks around the airfield perimeter. Guadalcanal was covered with coconut palms that produced oil-rich nuts in quantities that might be sufficient for experimental fuel production if he could develop a refining process using available equipment. Coconut oil had been used as lamp fuel and cooking oil for centuries, demonstrating that it was combustible and could burn in controlled conditions. The challenge was converting raw coconut oil into something that could power aircraft engines without destroying them in the process. Jake spent 3 days studying the chemical properties of coconut oil and comparing them to aviation fuel characteristics. Coconut oil had lower octane rating than aviation fuel, different volatility characteristics, and combustion properties that could cause engine knock or other performance problems if used without modification. But he also discovered that coconut oil had some advantages over petroleum-based fuels. It burned cleaner, produced fewer carbon deposits, and had natural lubrication properties that could actually improve engine longevity under certain conditions. The key was developing a refining process that would optimize combustion characteristics while minimizing potential damage. Working with equipment salvaged from destroyed aircraft and vehicles, Jake began experimenting with coconut oil refinement techniques that could be performed using resources available on Henderson Field. He needed to remove impurities, adjust volatility characteristics, and add compounds that would improve octane rating without requiring chemicals that weren't available on the island. The experimental work was extraordinarily dangerous. Fuel refinement involved heating flammable liquids to high temperatures, using improvised distillation equipment that could explode if operated incorrectly, and testing fuel mixtures in engines that could catch fire or suffer catastrophic mechanical failures. Jake worked alone during off-duty hours, using a hidden location in the jungle where accidents wouldn't endanger other personnel. His laboratory consisted of improvised equipment made from aircraft parts, aluminum tubing for distillation columns, engine blocks for heating vessels, and electrical components for temperature control. The first challenge was extracting oil from coconuts in sufficient quantities for meaningful experimentation. Jake improvised a crushing and pressing system using hydraulic components salvaged from aircraft landing gear, producing several gallons of crude coconut oil that could be used for refinement experiments. Raw coconut oil was thick, viscous, and had combustion characteristics that were completely unsuitable for aircraft engines. Jake needed to remove impurities, reduce viscosity, and modify chemical composition to create something that would burn properly in high-performance engines operating at combat power settings. His refinement process involved heating coconut oil to specific temperatures while removing water content and other impurities that affected combustion. He used distillation techniques learned during his experimental engine work at Ford, adapting industrial processes for field conditions using improvised equipment. The work required extraordinary precision under primitive conditions. Temperature control was critical for proper distillation, but Jake had no thermometers or precision instruments. He learned to judge temperatures by sound, smell, and visual cues that indicated proper processing conditions. After 2 weeks of experimentation, Jake had produced approximately 50 gallons of refined coconut oil that had combustion characteristics approaching those of low-grade gasoline. The fuel wasn't equivalent to aviation gasoline, but preliminary tests suggested it might power aircraft engines for limited periods without causing immediate catastrophic damage. But laboratory tests were meaningless unless the fuel could actually power aircraft engines under operational conditions. Jake needed to test his coconut fuel in a real aircraft engine, risking an explosion that could destroy valuable equipment and potentially kill him in the process. He selected a damaged P-40 that had been written off as unrepairable due to extensive battle damage. The aircraft would never fly again, but its engine was still functional and could serve as a test bed for fuel experiments. If the engine exploded during testing, the loss wouldn't affect squadron operational capability. Jake spent 3 days preparing the engine for coconut fuel testing, modifying fuel system components, and adjusting carburetor settings to compensate for the different combustion characteristics of his improvised fuel. The modifications required understanding engine operation at a level that exceeded standard maintenance training. The first test began at dawn on November 2, 1942, when Jake hand-propped the P-40's engine using 5 gallons of refined coconut oil mixed with small amounts of high-octane aviation fuel that he'd saved from previous operations. The engine started immediately, ran smoothly for 10 minutes, then began developing problems that indicated fuel mixture adjustments were needed. Subsequent tests involved refining his fuel mixture and carburetor adjustments until the engine could run on pure coconut oil without obvious performance problems. The work required weeks of experimentation, but eventually Jake achieved stable engine operation using fuel refined entirely from coconut oil and additives that could be produced on Guadalcanal. The breakthrough came when Jake discovered that adding small amounts of ethyl alcohol distilled from fermented coconut water could improve octane rating and combustion characteristics sufficiently to power aircraft engines for extended periods. The alcohol acted as an anti-knock additive that prevented engine damage while improving overall performance. By mid-November, Jake had developed a complete fuel production system that could convert coconut oil into aviation fuel substitute, using equipment and materials available on Henderson Field. His process could produce approximately 20 gallons of usable fuel daily, enough to keep several aircraft operational during critical periods when conventional fuel wasn't available. But individual experimentation was meaningless unless Jake could convince squadron leadership that his coconut fuel was safe and reliable enough for combat operations. Military regulations strictly prohibited unauthorized fuel substitutes, and using untested fuel in combat aircraft could result in court-martial for any mechanic who violated safety protocols. Jake approached Major Harrison with detailed documentation of his fuel experiments, including chemical analysis, engine test results, and performance data that demonstrated coconut fuel could power P-40 engines without immediate catastrophic failure. The presentation was comprehensive, but Harrison's response was predictably negative. "Sergeant, this is the most ridiculous thing I've ever seen," Harrison said after reviewing Jake's data. "You want me to authorize the use of coconut oil in aircraft engines worth more than most people make in 10 years. If those engines fail during combat operations, pilots die, and we lose aircraft we can't replace." Jake understood the Major's concerns, but he also understood that conventional aviation fuel wasn't available and wouldn't be for several weeks. Without his coconut fuel, the squadron couldn't fly combat missions regardless of engine reliability considerations. "Sir, we've got 12 aircraft that can't fly because we don't have fuel," Jake replied. "My coconut oil will keep them airborne until the next fuel convoy arrives. It's not perfect, but it's better than sitting on the ground while Japanese bombers destroy everything we've built here." The conversation was interrupted by air raid sirens warning of approaching Japanese aircraft. Harrison and Jake rushed to the nearest foxhole as 18 Betty bombers approached Henderson Field with 0 fighter escorts, beginning another systematic bombing attack that would destroy more American facilities and equipment. The bombing raid lasted 45 minutes and destroyed 2 more P-40s that had been parked near the fuel depot area. When the all-clear sounded, Harrison emerged from the foxhole and looked at the smoking wreckage of aircraft that could have been airborne to intercept the attacking bombers if they'd had fuel to fly. "Sergeant, you've got 24 hours to demonstrate that your coconut fuel actually works," Harrison said grimly. "If it does, we'll use it. If it doesn't, we're all dead anyway, so it won't matter. But I want you to understand that you're betting everyone's life on this experiment." Jake accepted the responsibility and began immediate preparations for operational testing of his coconut fuel system. He selected 3 P-40s that were in excellent mechanical condition and modified their fuel systems to optimize performance with coconut oil. The modifications involved carburetor adjustments, fuel line modifications, and engine timing changes that would maximize reliability while minimizing performance losses. The test flights began at dawn on November 18, 1942, when First Lieutenant Tommy Rodriguez took off in a P-40 powered entirely by Jake's refined coconut oil. The aircraft performed normally during takeoff, climbed to 10,000 feet, and completed a 30-minute test flight that demonstrated basic operational capability. Subsequent test flights involved progressively more demanding maneuvers that tested engine performance under combat conditions. The coconut fuel-powered P-40s through aerobatic sequences, high-speed dives, and sustained climbs that simulated combat operations. Engine performance was reduced compared to aviation gasoline, but the aircraft remained fully operational for missions lasting up to 2 hours. The real test came on November 20th when Japanese bombers approached Henderson Field and 3 P-40s powered by coconut fuel scrambled to intercept them. The combat mission lasted 90 minutes and resulted in 2 confirmed bomber kills without any engine failures or performance problems that compromised pilot safety. Word of Jake's success spread rapidly through Henderson Field and beyond. Other mechanics began requesting information about coconut fuel production techniques, and squadron commanders started planning combat operations that assumed coconut fuel would be available when conventional aviation gasoline wasn't. But Jake's innovation created new challenges that nobody had anticipated. Coconut fuel production required significant labor and resources that diverted personnel from other essential duties. The refining process was time-consuming and dangerous, requiring constant supervision to prevent accidents that could injure personnel or damage equipment. More importantly, coconut fuel had performance limitations that affected aircraft capabilities during combat operations. P-40s powered by coconut fuel had reduced maximum speed, lower climb rates, and decreased high-altitude performance that could compromise pilot survival during encounters with Japanese fighters. Jake spent weeks optimizing his fuel mixture and refining processes to minimize performance penalties while maintaining engine reliability. He experimented with different additive combinations, adjusted distillation procedures, and modified carburetor settings until coconut-fueled P-40s could perform nearly as well as aircraft running on aviation gasoline. The breakthrough came when Jake discovered that adding small amounts of benzene distilled from rubber tree sap could significantly improve octane rating and restore much of the performance lost when using coconut oil. The benzene addition required dangerous chemical processing, but the performance improvements were substantial enough to justify the risks. By December 1942, Jake had developed a complete alternative fuel system that could keep an entire fighter squadron operational, using only resources available on Guadalcanal. His coconut fuel had powered more than 300 combat sorties without a single engine failure that could be attributed to fuel problems. The success of Jake's coconut fuel system attracted attention from higher military commands that were dealing with similar fuel shortages throughout the Pacific Theater. Technical specialists were sent to Henderson Field to study Jake's procedures and determine whether his innovations could be applied to other locations facing fuel supply problems. Colonel Robert Sterling, Chief of Maintenance for the 5th Air Force, arrived at Henderson Field in January 1943 to evaluate Jake's fuel system personally. Sterling was skeptical that coconut oil could provide reliable fuel for sustained military operations, but he was also aware that fuel shortages were affecting combat capability throughout the Pacific. "Sergeant Murphy, I've read the reports about your coconut fuel experiments," Sterling said during their first meeting. "Frankly, it sounds like something out of a comic book, but if it actually works, we need to understand how it can be applied to other situations where conventional fuel isn't available." Jake provided detailed documentation of his fuel production procedures, including chemical analysis, engine test data, and operational results from 6 months of combat use. He also demonstrated the complete production process from coconut processing through final fuel refinement, showing Stirling that the techniques could be learned and applied by other maintenance personnel. Stirling was impressed by Jake's systematic approach and thorough documentation, but he remained concerned about the complexity and resource requirements of coconut fuel production. The process required skilled technicians, specialized equipment, and significant time investments that might not be practical for widespread implementation. "Your fuel works, Sergeant, but it's not simple," Stirling observed. "Training other mechanics to replicate your procedures would take months, and not every location has access to coconuts in sufficient quantities for meaningful fuel production. This is an interesting emergency solution, but it's not a replacement for proper supply logistics." Stirling's assessment was accurate, but didn't address the immediate reality facing forward combat units that couldn't wait for supply logistics to improve. Jake's coconut fuel provided a bridge solution that could keep aircraft operational during critical periods when conventional fuel wasn't available for any reason. The practical value of Jake's innovation became apparent in March 1943 when supply convoy delays left Henderson Field without aviation fuel for 10 days. Squadron operations continued normally using coconut fuel exclusively, demonstrating that Jake's system could provide reliable backup when conventional logistics failed. Jake's techniques were eventually documented in technical manuals and distributed to maintenance units throughout the Pacific Theater. His innovations influenced fuel conservation procedures and emergency logistics planning for the remainder of the war, providing options for situations where standard supply systems couldn't meet operational requirements. After the war ended, Jake returned to Texas and established Murphy's Engine Service, a specialty shop that focused on performance modifications and alternative fuel systems for agricultural and industrial applications. His wartime experience with fuel chemistry led to numerous patents and innovations that influenced civilian engine technology. Jake's most significant post-war achievement was developing ethanol fuel systems for farm equipment that could operate independently of petroleum fuel supplies. His innovations helped farmers reduce operating costs and maintain equipment reliability during periods when conventional fuel was expensive or unavailable. In 1965, Jake was contacted by NASA engineers who were developing fuel systems for spacecraft that would operate in environments where conventional fuel supplies weren't available. His expertise with alternative fuels and improvised refining systems provided valuable insights for space program applications. But Jake rarely discussed his wartime fuel experiments during his civilian career. The military had classified his procedures for security reasons, and his innovations weren't publicly acknowledged until military historians began studying Pacific Theater logistics in the 1970s. When asked about his wartime service, Jake would say he was a mechanic who helped keep aircraft operational under difficult conditions. He didn't mention that he had developed fuel from coconut oil, or that his innovations had enabled hundreds of combat missions that might not have been possible otherwise. In 1985, the Smithsonian Institution contacted Jake about his fuel experiments for an exhibit on wartime innovation and improvisation. Jake agreed to provide technical documentation and demonstrate his refining procedures, on the condition that the information would be used for educational purposes only. The exhibit revealed the full extent of Jake's achievement during the Guadalcanal campaign. Military historians realized that his coconut fuel system had provided crucial backup capability during critical periods when conventional logistics couldn't meet operational requirements. Jake's fuel innovations represented one of the most significant examples of battlefield improvisation during World War II, demonstrating that individual creativity and technical expertise could overcome supply limitations that threatened entire military operations. Staff Sergeant Jake Murphy died in 1998 at age 84, survived by his wife Betty and 3 children who had followed him into technical careers in engineering and automotive technology. His obituary mentioned his wartime service as an aircraft mechanic, but made no reference to the coconut fuel innovations that had influenced military logistics. His personal papers, donated to the National Museum of World War II after his death, included detailed documentation of his fuel experiments, showing the complete development process from initial concept through operational implementation. The papers demonstrated the extraordinary complexity of his chemical work and the remarkable success achieved using primitive equipment under combat conditions. In 2002, the American Society of Mechanical Engineers recognized Jake's coconut fuel system as one of the most significant engineering innovations of World War II. The recognition was the first public acknowledgment of his specific contributions to military aviation maintenance. The award citation noted that Jake's fuel system had enabled more than 300 combat missions during critical periods of the Guadalcanal campaign when conventional fuel supplies weren't available. His innovations had demonstrated that creative engineering could overcome logistical limitations that seemed insurmountable. But perhaps more importantly, Jake's achievement proved that breakthrough solutions often come from individuals who understand fundamental principles and apply them creatively when standard approaches fail under operational stress. October 14, 1942. 12 P-40 Warhawks sitting useless on Henderson Field because there wasn't a drop of aviation fuel left on Guadalcanal. One Texas mechanic with coconut palms and a chemistry set improvised from aircraft parts, developing fuel that kept an entire fighter squadron operational when conventional logistics failed. Jake Murphy proved that sometimes the most sophisticated technology is human ingenuity applied creatively to problems that seem impossible using standard approaches. His coconut fuel system achieved results that exceeded military logistics capabilities while demonstrating that mechanical knowledge could overcome supply limitations when lives depended on keeping aircraft flying under impossible circumstances. The innovation succeeded not because of advanced equipment or extensive resources, but because one person understood engines at a fundamental level and refused to accept that fuel shortages meant mission failure and certain death for everyone on Henderson Field. Jake's chemical knowledge and mechanical intuition created solutions that worked when conventional procedures offered no alternatives under combat conditions. His achievement represented more than just successful fuel substitution under emergency conditions. It demonstrated that individual expertise and creative problem-solving could overcome logistical limitations that seemed insurmountable using standard military procedures. When supply systems failed under combat stress, human knowledge and determination provided solutions that no logistics manual could have anticipated. Jake's coconut fuel innovations influenced military maintenance procedures for the remainder of the war and provided theoretical foundations for alternative fuel development that wouldn't be fully explored until decades after his original breakthrough on Guadalcanal. His techniques proved that creative engineering could exceed the capabilities of conventional logistics when applied with precision under extreme pressure. The system's success demonstrated that breakthrough innovations often come from individuals who understand fundamental principles and refuse to accept conventional limitations when human lives depend on finding solutions that work regardless of official specifications or approved procedures. 12 aircraft kept flying for 6 months using fuel refined from coconut oil under impossible conditions. 300 combat missions powered by improvised fuel that shouldn't have worked. And the realization that creative problem-solving matters more than regulations when survival depends on making things work against all odds.